Imagine a desert, silent except for the wind. Stretching to the horizon, ready to go, are the ghosts of aviation's past. Thousands of retired airplanes parked in neat rows under a relentless sun. This is the boneyard. For decades, this has been a place of rebirth. These metal birds, mostly aluminum, are a recycler's dream. With a bit of brute force and a lot of heat, up to 90% of their metallic skeletons can be melted down and forged into the new products, from soda cans to car parts. It's a dirty but remarkably efficient final act. But a new ghost is beginning to haunt these graveyards. It's sleeker, darker, and fundamentally different. It's the Boeing 787 Dreamliner, the Airbus A350. These aren't just metal tubes with wings. They are marvels of material science, sculpted from carbon fiber composites. These materials are the reason you can fly farther on less fuel, with more comfort than ever before. They are stronger than steel, yet lighter than aluminum. They are, in a word, revolutionary. And that revolution comes with a dark secret. While we celebrate their efficiency in the air, we are completely unprepared for their death on the ground. When these carbon fiber giants reach the end of their life, they don't join the simple cycle of melting and rebirth. They become a problem, a mountain of high-tech, incredibly complex waste that we are only now learning. To understand the problem, you have to understand the material. It's called CFRP, carbon fiber reinforced polymer. Picture this: threads thinner than a human hair, but woven from pure carbon atoms, giving them incredible tensile strength. These threads are woven into complex fabrics, like a high-tech textile, and then infused with a polymer resin, essentially a super strong plastic glue. The fabric provides the strength. The resin provides the shape and rigidity. Together, they create a material that changed everything. See, before composites, engineers had a simple trade-off: strength or weight. You could build a plane out of steel, but it would be too heavy to fly efficiently. You could use aluminum, which was a brilliant compromise, but it had its limits. It corrodes. See? It suffers from metal fatigue after thousands of cycles of pressurization. Composites shattered this paradigm. They don't corrode. They are phenomenally resistant to fatigue, and crucially, they allow for designs that were physically impossible with metal. The Boeing 787 Dreamliner is the ultimate testament to this. In older jets, like the 737, composites made up maybe 5% of the airframe. The Dreamliner, it's a staggering 50% composite by weight. The entire fuselage isn't riveted metal panels. It's single, massive, barrel-shaped sections of carbon fiber. The elegant, soaring wings that flex in turbulence, pure composite. This wasn't just an upgrade, it was a fundamental reinvention of how to build an airplane. But here's the deal with it. That beautiful, seamless fusion of fiber and resin is precisely what makes it a recycling nightmare. Aluminum is a simple element. You melt it down, the impurities burn off, and you're left with pure aluminum again, But how do you unweave threads that have been permanently baked into a plastic tomb? How do you separate the valuable carbon fibers from the worthless, hardened resin without destroying it For years, the answer was simple. For a long time, this wasn't a crisis. The number of composite heavy planes retiring was a trickle. But that trickle is about to become a flood. The first generation of Dreamliners and A350s are now entering their second decade of service. In the next 10 to 15 years, thousands of these aircraft will be taken out of the sky. A single retired 787 represents about 35 tons of carbon fibre composite that needs to be dealt with. Now, multiply that by the thousands of planes in the global fleet. Currently, our best case scenario for most composite waste is processed generously for recycling. But it's more accurate downcycling into human. The massive composite sections are shredded by industrial grinders into small chips. The valuable, long, interwoven fibres that gave the material its incredible strength are destroyed in the process. What's left? A filler material. A kind of carbon fibre confetti that can be mixed into concrete or plastics to add a bit of stiffness. It's the equivalent of taking a Rolex watch and melting it down for a few cents worth of scrap metal. You've recovered a tiny fraction of its original value and destroyed all of its sophisticated structure. The worst case scenario, and for a long time, the most common, is the landfill. These advanced materials, the pinnacle of human engineering at our, are simply buried in the ground, where they will sit, inert and undegrading, for centuries. We took a material designed to last for 40,000 flight hours at 35,000 feet. The challenge, then, is an alchemical one. How to turn this high-tech trash back into treasure. The goal is to liberate the pristine, long-strand carbon fibres from their resin prison, with this allowing them to be re-woven into new, high-value products. And scientists are pursuing two main paths to achieve this. The first is the brute force method, refined. It's called pyrolysis. In its crudest form, you place the composite in an oxygen-stable oven and bake it at extremely high temperatures. The resin vaporizes and burns away, leaving the carbon fibers behind. The problem is, this intense heat is like cooking a delicate steak with a blowtorch. It damages the surface of the carbon fibers, weakening them by up to 50%. They're still useful, but not for aerospace grade applications. It's also spectacularly energy intensive. But a new generation of pyrolysis is emerging. Think of it as a low and slow barbecue instead of a raging inferno. By carefully controlling the temperature at a lower range, around 400 to 600 degrees Celsius, engineers can thermally decompose the resin more gently. This surgical approach preserves much more of the fiber's original strength. The recovered fibers are not just filler, they are a genuine industrial material, ready for a second life. In car bodies, wind turbine blades, or high-end sporting goods. This is the technology that promises to get us from a dismal 10% recycling rate to a more respectable 50%. The second, more elegant path is chemical. It's called solvolysis. Instead of burning the resin off, this process uses specialized solvents or heat and pressure to chemically dissolve it. Imagine soaking a fossil in a specific acid that dissolves the rock but leaves the delicate bone intact. That's solving the chemistry is only half the battle. You also have to build the factory. Recycling an old aluminum 747 is a messy, visceral process. Giant hydraulic shears, nicknamed the can opener, tear through the fuselage like it's paper. But you can't do that with a Composites 787. Shredding carbon fibre creates clouds of fine, airborne dust. That is a serious respiratory hazard and can short-circuit electronics. The disassembly plant of the future will look less like a scrapyard and more like a robotic surgery theatre. Instead of shears, precision robotic arms wielding high-powered lasers or water jets will meticulously slice the fuselage and wings into manageable pieces. This process contains the hazardous dust and preserves the large woven sections of a composite material, making them ideal for the pyrolysis or solvolysis reactor. Once disassembled, another challenge emerges: identification. Not all composites are created equal. An Airbus A350 might use a different resin system than a Boeing 787. To recycle them effectively, you have to know exactly what you're dealing with. The solution is straight out of science fiction. Advanced spectroscopy. Automated systems will scan each panel using light to analyze its unique chemical signature and sort it accordingly. This level of granular sorting is critical for producing a high quality but consistent recycled product that manufacturers can act here. We arrive at the $1 trillion question. We have the technology, or at least a clear path to it. We understand the scale of the problem. But does it make economic sense? The aerospace industry has set an ambitious goal to create a closed-loop recycling system for composites within the next 15 years. But two brutal realities stand in the way: energy and cost.
The transition to the circular model is our only path forward.
The laws
Agreed,
of thermodynamics
but the logistics in Sector 7 remain a challenge.
Locking carbon fibres into a resin matrix is an energy-intensive process. Unlocking them, whether through pyrolysis or solvolysing, also requires a massive amount of energy. The critical question is, does the energy spent recycling equal the energy spent creating virgin carbon fibre? Right now, the answer is maybe. If the recycling process is powered by fossil fuels in Europe, we could end up in a situation where the green solution has a larger carbon footprint than the problem it's trying to solve. The sustainability of composite recycling is directly tied to the availability of cheap, abundant, renewable energy. Then there's the price tag. As of today, even high quality recycled carbon fibre is often more expensive than its virgin counterpart. Manufacturers, especially in high volume industries like automotive, are driven by cost. Why would a car company, choose a more expensive recycled material, even if it's slightly better for the planet, when cheaper, brand new fibre is readily available, without government incentives like carbon taxes or regulations mandating? We began in the boneyard, surrounded by the ghosts of aviation's past. We see now that the sleek, black-winged aircraft of our present pose a far more complex question about our future. The Boeing 787 Dreamliner, the aircraft that promised a new era of efficiency,
that our sustainability
has unintentionally
initiatives are
forced
working.
us to confront
As you can see,
the full
we're
life cycle
making progress
of our creations.
every day.
The solution won't be a single silver bullet. It will be a messy, interlocking system of innovations. It will require breakthroughs in low-energy pyrolysis, scaling up chemical solvent lysis, and building a global network of robotic disassembly plants. But more than that, it will require a seismic shift in economics and design philosophy. And it will demand that engineers, from the very beginning, design not just for an aircraft's life, but also for its death. The legacy of the carbon fibre revolution could be a story of unparalleled efficiency, followed by an environmental reckoning. Or it could be the catalyst that forces one of our most advanced industries to finally close the loop, proving that technological progress and true sustainability can and must fly together. The monumental task of unbuilding a titan of the sky begins with a single, calculated cut. Precision is paramount. Every salvaged component is a victory against waste. The digital ghost of the aircraft awakens. Its history, now the key to its future, value. The carbon fibre paradox, a material born of incredible strength, presents a formidable, brittle problem for the future. The race is on, not for speed in the air, but for a breakthrough on the ground. The final frontier isn't space, but a closed loop, a sky that endlessly renews itself.